Hey everyone, today we are solving Leetcode question 3302 and this is marked as medium. Alright, and for this particular problem we have some learnings. Uh, I will say this for this problem we'll think in one way, but at the end we get to know that whatever the way we are thinking is wrong. Actually, we need to think in the other way. Okay, let me set the outline of this video. First of all, we will see the problem. Next, we will see the examples. Next, we will see the constraints of the problem. Next, I will show you the thought process 1 and thought process 2. And also over here, um, for the thought process 1, we'll do the coding part, and after that we'll see what are the loopholes for this thought process 1. Next we go to thought process 2 and we will do coding for this thought process 2, and at the end we will take away some learnings from this problem. All right, we are gonna do coding in CPP, but anyway the logic is same. You can do in whatever language you are comfortable with. All right, now let's go to the question and let's read the question clearly once. Question is saying that find the lexicographically smallest valid sequence. You are given two strings word1 word2. A string x is called almost equal to y if you can change at most one character in x to make it identical to y. It means that suppose we have the let's say we have the string a b. Let's say this is x and we have the y as some z a b. Now we can able to say that these two are almost equal because we can change at most one character in this one. In this case we can change this character to z and these two are equal, so they both are identical to almost equal to each other, or x is almost equal to y. This is the meaning of this sentence, and in the question they given that a sequence of indices seq is valid if the indices are in sorted order, if the indices are sorted in ascending order, and concatenating the characters at these indices of word1 in the same order results in a string that is at most equal to word2. That means let me take this example. Over here what they are saying is that we need to select a sequence from this word1, and whatever the resulting sequence, that word should be uh, at most equal to almost equal to word2, and it have so many ways. Like we can take the sequence over, we have v b c c a, this is the sequence, and now we need to have the sequence of length 3. That is obvious, why length 3. And now suppose we can take this sequence, or we can, okay, in this one there is only one possible sequence we can take. Let me do one thing. Let's say the sequence will be this one, v b c a v c a. Okay, let's assume this is the sequence. This is the word1 and we have the word2 as a b c. Another thing is that from this word1 we need to select a sequence of length word2 dot length, or we need to take a length of 3 sequence from this word1, and such that the resulting sequence or the string should be almost equal to word2. Now we can do this in for this one there may be many answers. We have VBC over here, or we can also have ABC over here, and I think, yeah, that's it. Now if we observe carefully, this is almost equal to this one because we can able to change V to A and these two are equal. All right, or we can also able to change this V to B and these two are almost equal. Now what they are asking is that they want lexicographically smallest valid sequences of indices. They want the indices and they should be lexicographically smallest. That is, we need to have let's say have 0, 1, 2, 3, 4, 5 as the indices. One answer would be 0, 1, 2. Other answer is 3, 4, 5. Now the lexicographically smallest means we need to take that sequence which has the uh, less index number, in this case 0, 1, 2, not 3, 4, 5. Now you may also ask that what if the let's say we got two answers, they have 0, 1, 2 and 0, 2, 3, then the lexicographically smallest answer will be this one because these two are same. We'll go to this one, since this is the smallest we'll take this one as the answer. I hope this clears what they mean by lexicographically smallest valid sequence of indices. All right, now coming to the question, they asked us to return an array of size word2 dot length representing the lexicographically smallest valid sequence of indices, and if no such sequence exists we will return an empty array. And also look into this note that's saying that the answer must represent the lexicographically smallest array which we have seen just now, not the corresponding string formed by those indices. That is, we need to return the array of indices, not the string that is formed by those indices. It means that we need to return, if we take this example, we need to return 0, 1, 2, but not V, B, C. They are expecting us to return the indices array. All right. Now, if we just look into some of the examples over here, for this VBC and ABC, this is the output. I think this example is covered over here, and let's take this example BAC DC. We have the word1 as BAC DC, BAC DC, and word2 as ABC. Now in this one we need to select a sequence of length 3 and whatever the resulting string of the sequence in the same order, that should be almost equal to word2. Now here we can take one sequence as the A, D, C. I think this is the only option over here. We can change that most one, so we'll change this to B and this will be equal to ABC. Right, see here 1 and 2, 4, sorry, my bad. We can also take this one A, C, C, because we can change C to B over here. So the lexicographically smallest thing here is 1 to 4. Remember carefully that we need to return the lexicographically smallest valid sequence of indices. There may be multiple array of indices where the resulting sequence of the string is almost equal to the word 2, but we need to return the lexicographically smallest valid sequences. This is the important point over here. And now we'll also look into this case where there exists no sequence in word 1. Suppose you take this one and you have this word 2. No matter what sequence you take, any sequence you take, it will only come with all the characters with A. Now in this one we have 3 different characters. We have also A over here, but the thing is that we have B and C as 2 different characters. Now we can change at most 1 character, which will result in the number of unique characters in this string as 2, whereas in this string number of unique characters is 3, which means that we cannot have any sequence that is almost equal to word 2. So we will output an empty array. Alright, now we have looked into what the problem is, and we have looked into the some examples. Next we will look into the thought process 1. But before looking into the thought process 1, if we observe the constraints that here we have the word1 dot length as 3 into less than or equal to 3 into 10 power 5, as well as word2 dot length as 3 into 10 power 5. Now let's say n is the word1 dot length. Word1 dot length, let's say it is n. Now if you write an algorithm that is big O of n square, which will be 3 into 10 power 5 whole square, which will be 9 into 10 power 10. Now in the Leetcode or in the code forces also, remember that if your time complexity is exceeding 10 power 10, then that will give you the time limit exceeded or runtime error. All right, so one thing is obvious here is that big of n square solution will not work. Now from logic we can say that maybe we need to have the big O of maybe n log n solution or big O of n solution. We'll write the algorithms to get the time complexities as this one. Alright, now first we will look into the general thought process everybody will get. Then after we will see what is wrong with that thought process and why that thought process will not work for this question. Later we will move on to the next algorithm, which will not give time complexity big O of n square. Alright, now let's move to the thought process 1. Alright, if we come into the thought process 1, that so everybody first of all will think that we are generating or we are looking into the sequences of the word 1 or the subsequence in the word 1. One can do in a brute force way is that, now first we'll this thought process is brute force. Now one can think like to generate all subsequences or sequences and find the smallest lexicographically smallest answer which will satisfy their given conditions. That is, the sequence is almost identical to word 2 and that is lexicographically smallest thing. Now one thing here is that to generate all sequence it will take exponential time complexity. And for checking this one, since we are checking in all the sequence, this is also is going to take the exponential time complexity. Now just for practice, uh, we'll see the thought process one now, like how to go in this approach. Now one thing is that, so we have the V, B, C, A, V, C. What we will do is that, let's say we have the sequences is nothing but each character we have two choices, either we can take it or not take it. All right, now suppose we are at V. One thing we can do is that we can take that one and it will give us the V, and we start with an empty sequence, and if we not take that one, it will give an empty sequence. Now our index will go to the next one, and again it have two choices, either we can take it or not take it. Here also we can take it or not take it. If we take it, then it will be VB. If we not take it, it's just V. And here if we take it, it's B. If we not take it, it's just an empty string. Now we again move our pointer to C. Again this have two things, either we can take it or not take it. Similar, this have two ways, take it or not take it. This have two ways, take it or not take it. This have two ways, take it or not take it. Now we will stop at certain point. Let's say, let's write this particular stage over here. Next we'll observe, suppose we have take it, then it will be VBC. If we cannot take it, it's VB. If we take it, it's VC. If we cannot take it, it's just V. If we take it, it's BC. If we cannot take it, it's B. If we take it, it's C. If we cannot take it, just an empty string. Now again we move this pointer to the next one. Again for each one we have two things, either we can take it or not take it. But observe that we only need a sequence of length which is equal to word2 dot length. That is, we will stop if the current sequence length, if it is equal to the word2 length, then we cannot explore further. Like in this case, we have got a sequence of length 3, so it is no need to explore the further cases. We just need to check whether if this sequence of length 3 is almost equal to the word2. All right, and also one more case is there, that if we observe this branch over here, we may end up in getting to the out of the index. That is, if our index is equal to word1 length, then we will return an empty string maybe. Okay, we'll look into this base case in detail when we're writing the pseudocode. All right, now what are the variables are we taking over here? We are taking one variable index over here, and at each state we also have the current sequence. It is current sequence also we have there, and I think only these two the only variables, and we have drawn the recursion tree. Next what we will do is that we'll code whatever the discussion we have done into the pseudocode, and we'll implement this in the Leetcode platform. All right, now If we talk about the pseudocode, let's say we have the function solve, then it will have the word1, word2 obviously, and the index and the current string. As discussed over here, we have the index and the current string. Now one thing, the base case is that if the current size is equal to word2 size, then let's say we have a function is almost equal what this will do is it will take two sequence x and y, and it will return true if x is almost equal to y, otherwise it will return false. And over here what we will do is that it will return the is almost equal of current comma word2, right? And this is one base case. Now other base case is that if index equal to word1 dot size or word1 size, then it needs to return nothing, right? Let's say we are returning the string. I will tell you why we are returning the string over here. Since we are returning the string over here, what we will do is that we will return an empty string if the current sequence is not almost equal to word2. Otherwise, if it is equal, we will return the current sequence itself. All right. I know they are asking for the vector of indices. I will show you how to do this one. First we will do this one. I'll tell you how to do that one. Now if index equal to word1 dot size, then we will return an empty string, and we'll return an empty string. All right. Now we have, for a particular index, we had two choices. Either we can take that one, let's say we have the string take and string not take. Let's say we have taken that one, then our solve function, if we taken that one, then we have the solve word1, word2, and the index plus 1, and the current will be, since we are taking that one, current plus word1 of index. All right. Now here the thing is that if the current comma word2 are almost equal, then we will return the current sequence. Otherwise we'll go for not take case, and here we also do the same thing, except here word1, word2, index plus 1, except here we'll just pass the current since we are not taking that one, and we will return the empty string if not take is not almost equal to word2. Otherwise we will return the sequence or the current thing. All right. Now, since they are asking us to find the indices, what we will do is that we will take an empty array and we will pass it by reference in the solve function. We have over here the an array, and since if we are taking this one, if we are taking that one, what we will do is we will array dot pushback of index since we are taking that one. Suppose this line is not executed, it means for the take case that index is not applicable. So what we will do is array dot pop back since we are not considering that element. And yeah, I think based on this one, automatically the indices will get updated according to this function. All right, now we'll code this function in the lead code and we'll see whether this works or not. All right. All right, now we'll code whatever the recursion part I have told in the tab. Now I know I haven't told clearly, but I hope you will follow. And also one more thing is that I haven't told how to uh, write the is almost equal function that we will do over here, which is not a hard thing. It is a easy thing. Okay. Now first of all, okay, sorry. First of all, we will write is almost equal. For this one, we require two strings x comma y. Let's say we have the string will pass by reference for the string word1, string ampersand word2, and over here, according to the question, if we can change at most one character in the word1, and if word1 and word2 are equal, then we will return true, otherwise false. Now for this one we will keep a count, that is number of distinct places where the characters in word1 and word2 are different. If the number of distinct indices are greater than 1, then it means it is false, otherwise we will return true. So we'll code that one up. So we'll have the count as 0, and let's say we have the size of the words are word2 dot size. Now we will iterate through the uh, words int I equal to 0, I less than n, I plus plus. If cnt is greater than 1, it means will return false, because we can change at most one character. Otherwise, uh, we'll check if uh, word1 of I, if it is not equal to word2 of I, it means they both are different, and we increase the cnt plus plus, and we will return true over here. If the number of distinct, sorry, one more thing is that here we again need to check if cnt is less than or equal to 1, then only we need to return true, otherwise we need to return false, because for the last index this won't execute, right, this line. So we'll return this one. I think this is a easy function, you can write it by yourself. Now we'll write the main function. um, so main function, we have said that the main function will return the string where the solve. We have the string ampersand word1, and we have the word2, we have the index, and we'll also pass the indices vector, vector of int ampersand indices. All right. Now first thing is that if I think we also need to send the current uh, string ampersand current. All right. If current dot size is equal to var2 dot size, then we will return is almost equal of current comma var2, right? And also if index is equal to var1 dot size, we will return an empty string. All right. Next we have the two cases. Next we have the two cases. Next we have the two cases, that is we can take, if we take then the current will be current plus var1 of I. Now here string take equal to sol of var1 var2 index plus 1 current and indices. Now here what this is saying is that if take is not equal to an empty string, then it means we can return the current. That means if we have taken the first character and let's say uh, um, what this will give is that um, what I'm saying is that if this is not equal to uh, empty string, that is so we'll return the current over here because if it is not equal, then it means to say that we have the lexicographically smallest we have found out and we'll return the current. Otherwise, for not take case, current dot uh, back, and one more thing is that we also need to push the current index into this one, indices dot push back of index, and over here indices dot pop back. Now string not take equal to sol of var1 var2 index current indices, and will return here uh, not take. And yeah, I think this is a function. Now the main here what we'll do is that we'll define the vector of int indices and the string current as empty string, and we'll run this function solve, which will be var1 var2 and index is 0 current indices. All right. Now here we will return indices. If we run this code, sorry, there is a compilation error, is almost equal type bool to the function. Okay, here we need to return the string, right? We'll do one thing. Um, if it is possible, then we will return current, or else we'll leave it as it is, or else if it is the case, we'll return that one, else we'll return an empty string over here. I think this should work fine. All right, current, all right, my bad. I think, all right, current plus word of index, we'll run again, we'll get one more compiler error. Yes, last executed input, current equal to dot word1 of index. One thing over, one thing here is that here it should be index plus 1. And it have passed the test cases, but this recursion thing is will take exponential time complexity. So for what, so for word1 of length near 3 into 10 power 5, it will give time limit exceeded. We can see over here. See, it's giving the time limit exceeded. So we need to think of other thing. One thing we can do in the recursion thing is that we will try to memorize the thing. But here uh, I'll go to my iPad and I will tell you why this won't work. Like memorization, why it won't work. All right. All right. Now I will tell you why this recursion part we can't memorize for this one. Okay. Now if we see what are the changing states of the recursion, those are the index and the current, right? And we have the index will go from 0 to uh, word1 dot size, and if we see the current, it is a sequences in the word1, and there will be 2 power word1 dot size number of sequences. This is exponential, and we cannot able to create an array or a data structure which has the size this much. Okay, so we can do memorization here for this recursion, because we cannot create enough space to remember all the states. All right. And also, even there is another approach for solving this recursion, that is we have the simple solve function. We have the index I, index j, and we have, let's say, a variable changed where I is the current index in w1, j is the current index in w2, and changed means that whether we have used our one free change. Okay, and at every step, if word1 of I equals to word2 of j, then we can just take it, because we need to have the lexicographically small indices, and if they don't match, we have a choice: either we can use our free pass or we cannot use our free pass, and we'll try both the things. we'll try both the things and we'll write the code. But the catch even for this one is also that I will go from 0 to word1 dot length or size. J will go from 0 to word2 dot length. If you see the constraints, that word1 will less than or equal to 3 into 10 power 5. In the worst case, we need to have an array. uh, we need to have an array uh, which have the every pair of indices I comma j, which will be, let's say the array is m by n, then m equal to 3 into 10 power 5, n equal to 3 into 10 power 5, and mn equal to 9 into 10 power 10. And for this space, we cannot able to create this much of space using the dp array. So even if we follow this method also, we cannot memorize this one, because we can't able to create this much amount of space to remember all the overlapped subproblems. So the recursion part will work obviously, but the memorization part, this won't work, and this should be important, and you need to understand why this won't work, because we cannot able to create this much amount of space. All right, so till now everyone, what they will do is that they will go for the recursion for this kind of problems. Next they will memorize that one, and after that they do the bottom up or top down approach, and they will space optimize this one. But here in this problem we cannot do the memorization, so we need to think of the other approach. This is where we'll go to the thought process 2. all right Welcome to thought process 2. And before moving to thought process 2, will we came to thought process 2 because the previous thought process 1, it will give the memory limit exceeded, because we cannot able to create an dp a data structure with the what are the number of states over there, that will give the memory limit exceeded. Now comes to this thought process 2, that here in this case dp is out. Now the question is, how do we solve this one? All right, one thing is for sure, that the answer will not be big of n square, where n is the word1 size, and the answer definitely for sure it will not be also big of n log n, because there is no sorting thing or binary search thing required over here, because we are working with the sequences. So we will discard these two time complexities. Now according to the now the obvious solution of the time complexity bigger of n. Now we'll wait a second and we'll think the dp failed here and we want the big of n approach. If we look carefully in the problem description, they have this thing called I'll write it down, lexicographically smallest, and this is the main magic word over here. That is whenever we see smaller indices or earliest sequence, it means this is a massive hint, and this is a massive hint for the which approach? Greedy approach. You're right, it's greedy approach. So here we should not use the db approach, rather we need to go for the greedy approach. All right. So greedy means we want to grab the first valid character we see going from left to right. If word1 of I is equal to word2 of j, then we will take it because it's always optimal. But what if they don't match? Then in that case we have two choices. uh, we want to use our one free change right now to keep the index as small as possible, but we can only do that if we are 100% sure that the rest of the word 2 can be perfectly found in the rest of the word 1. So we need a way to look into the future. All right, that is, I'll repeat it once again, that we need to use one free charge right now to keep the index as small as possible, as small as possible. But we can only do that if we are 100% sure that the rest of the word 2 can be perfectly found in the rest of the word 1, right? So somehow we need to look into the future, that is the rest of the word 2 should be present in the rest of the word 1, right? So I will write whatever the thoughts over here. First thing we got over here is that since it is lexicographically smallest, it means we need to go for the greedy approach. Second one, if match, then take it immediately. Third thing, if they don't match, we need to ask here a question: can we use one change? The answer will be yes, if rest of word 2 perfectly matches the rest of word 1, otherwise we cannot use that one. Okay, and here we also, one thing is that we need to see the future. We need to see the future because here we need to check this whether this happens or not. So this is pointing towards this one. We need to look into the future, right? So now we'll go to the solution part of this one. All right, now the solution part here is that the trick comes here is that we'll do greedy plus pre-computation. I'll tell you what this pre-computation here means. We will define one suffix array, okay, where suffix of I, this will tell us the longest uh, longest chunk of word 2 that perfectly matches match the word 1 from the starting index I to everything. That is, let's say we have the word 1 over here, sorry, we have the word 1 over here, and we have the word2 over here, and for a particular index I over here, we'll look into this part and we'll check what is the maximum length from this side, that is perfectly in this part, okay, from I, that is suffix of I. All right, now we can do this big of n in time complexity, that is we have the I from n minus 1 to 0, and we have the suffix of I that is equal to suffix of I plus 1, that is for this the answer will be the answer of this one plus this one according to this diagram or visualization, and that is we are carrying the previous best, we are carrying over the previous best also over here. Okay, now over here, and our j will start from the m minus 1, and here m is the size of word2, n is the size of word1. All right, and here we'll write one for loop, maybe if j is greater than or equal to 0 and word1 of I equal to word2 of j, then we'll increase our suffix of I, and also we'll do j minus minus because it is get covered over here, right? Okay, now after that one we'll construct the answer array. Okay, now we have done the pre-computation part. Here we have constructed the suffix array or sov of I. Now here comes the main thing is greedy construction, right? Now this is simple. We are at index I in the word1 and index I in the word2. If word1 of I is equal to word2 of j, then we will take it, and because it is always optimal for the lexicographically smallest indices, and we will move the pointers to the right side. And if this is not the case, that is if w1 of I is not equal to w2 of j, if it is not the case, then we can only take it if we have not, we can only take it if we do not, if we have not used our one change yet, that is we are left with the one change, we are not using it, and also the remaining word in the word2 is m minus 1 minus a, and this should present in the word1, right? In the word1 from the I plus 1 index, that is in the word1 from the I plus 1 index over here, this should completely present in this one, that is in the word2 we have the j from j plus 1 over here, this should completely present in this one. And we can check this in big O of 1 time complexity by just if suffix of I plus 1 is greater than or equal to m minus 1 minus j, it means this is completely in this one, then we can take it and we can take it, right? Now if we write the pseudocode for this one, if we write the pseudocode for this one, let's say we have the answer array, and let's say we have the boolean changed equal to false, that is we haven't used our one free change, and the j will starts from 0 and I is also starts from 0. We'll have I equal to 0 till n minus 1 and also uh, maybe we can write a bit clearly: I equal to 0, I less than n, and z less than m, and I plus plus. Over here we have two cases: if what1 of I equal to what2 of z, then we'll take that one, that is answer dot push back of I comma, we'll do z plus plus over here. Else if we have the free change, that is we haven't used that one, and the remaining what2 is still present in the remaining what1, that is checked based on this condition, then we can use that one and we'll modify the change as true because we're using that one, and we'll push that index into the I and we'll do z plus plus. And after this while loop we'll check that if answer size is equal to m, then only we will return m, otherwise we will return empty array. I think this makes sense because we need to have the sequence of length of the word2, right? Now if we talk about the time complexity of this one, for the pre-computation it is taking big O of n, and forward pass and the backward pass, sorry, in the forward pass of this one, I think this also is taking big O of n, big O of m. Maybe we'll have the big O of max of n comma m. Given the question, it is n is the maximum, so the time complexity is big O of n, and the space complexity is also big O of n because we are creating the suffix array. We are getting a suffix array. So we'll code this in the code editor, and I think this is the solution. The main key takeaway from this question is that we need to observe whether we can create an DP array or not. If we cannot create a DP array, then we need to search for the things they are saying in the question that may point out to the other questions, other patterns, that is here in this case greedy. All right, now yeah, I think this is the main key takeaway. Before implementing anything we need to check whether we can go in the DB or not. If we cannot go in the DB, then mostly we'll go in the greedy. I think this is the solution for the question. And yeah, thank you. Maybe I can have explained better. From the next video I'll improve myself, and that's it for this video. I will see you in the next one. Until then, code daily and bye. So we'll code the greedy approach now. Okay, so in the greedy approach we have taken that n and m as the size of the word1 and word2, and after that we have constructed the suffix array, so which is the vector of int sub of n plus 1 comma 0, and over here we will take the z from m minus 1, right? So we'll just follow whatever the pseudocode I have written. Point I equal to n minus 1, I greater than or equal to 0, I minus minus, and sub of I equal to sub of I plus 1, and if j is greater than or equal to 0, and what one of I equal to what 2 of j, then we'll add sub of I plus plus and j minus minus. So with this one, this array will get constructed. Next, we will construct the vector array using the greedy approach, which will be vector of int ans, and we also take one variable bool changed which equals to false, and z equal to, again we'll start from beginning now, and here point I equal to 0, I less than n, and n and z is less than m, do I plus plus. Now if word 1 of I equal to word 2 of z, then we will take it, that is answer dot pushback of I, and we'll do the j plus plus, um, else if uh, we haven't used the one lifeline, not changed, and sub of I plus 1 is greater than or equal to m minus uh, j minus 1, and we'll use this one for a greedy approach, and we'll make this true, and we'll answer dot push back, we'll take this one I and do z plus plus. And after this for loop we'll check if answer dot size, if it is equals to m, then we'll return answer, otherwise we'll return an empty array or empty vector, right? I think this should work fine. Now the time complexity for this one is, for this one big O of n, for this one is big O of n, and time complexity is big O of n, and space complexity is also big O of n. So for this one we cannot build the all the state spaces which will give memory limit exceeded. So at the time we need to get in our mind that we need to follow the greedy approach. Now let's try to run this one, and compilation error suf, all right. Where is that one? Okay, else if this is suf, let's run it one more again, and yeah, there you go. Now if we submit this one, and yeah, that's it. So that's it for this one. uh, I'll upload a similar kind of videos, but next time I'll improve my whatever the presentation skills, everything. And thank you for watching. Bye and have a great day.